In the last video we saw that if we have 3 points, then there exists a unique circle that passes through these points. This means that if we take a fourth point, it will most likely not lie on the circle around the 3 points, meaning that there doesn't exist a circle that passes through all the 4 points. But sometimes there is, namely when the fourth point lies on the circle defined by the first 3 points. A quadrilateral, such that there exists a circle that passes through all 4 of its vertex, we're going to call cyclic quadrilateral. In this video we're going to prove some of the properties of the cyclic quadrilaterals, and we're going to see ways in which we can prove that the quadrilateral is cyclic. In the previous video we proved that if this angle is gamma, then this angle here is twice as much, so 2 times gamma, where this is the center of the circle. And hence, if we take another point on the circle, then the angle which it's going to make is also going to be gamma, because this angle here is always twice as much as this angle here. And therefore, for a cyclic quadrilateral, such as this one, we always have that this angle equals this angle. So in any cyclic quadrilateral, any 2 angles that point towards the same arc are equal. Here are the 2 angles, they point towards this arc, so they are equal. Similarly, if this angle is beta, it points towards this arc, and so this angle here is also beta. Similarly, this angle is alpha, then this angle is alpha because they both point towards this arc. And if this angle here is delta, then this angle here is also delta because they point towards this same arc. Another thing that we saw in the previous video is that if we have an angle gamma, and of course now this angle is 2 times gamma, then the angle down here that points to the larger arc instead of the smaller arc is going to be 180 minus gamma, which is half of this angle here pointing towards the same huge arc, which is 360 minus 2 gamma. And hence, if we have a cyclic quadrilateral, then the sum of any 2 of its opposing angles is 180 degrees. So if this is gamma, this is 180 minus gamma. And of course, if this angle here is beta, then this angle here is 180 minus beta. To recap, we discovered 2 properties of the cyclic quadrilateral. First looks like this, and second looks like this. Now we're going to prove that these properties work the other way around, which means that we can prove that a quadrilateral is cyclic if we show that one of these 2 properties holds. For example, if we don't know that this quadrilateral is cyclic, but we do know that this angle is gamma and this one is 180 minus gamma, then it will follow that there is a circle around these 4 points. And similarly, if we know for some quadrilateral that this angle equals this angle, then we will show that there exists a circle that passes through all 4 points. We're first going to start with this property. Suppose that there is a quadrilateral such that this angle plus this angle is 180 degrees. Now we're going to prove that it's cyclic. Well, suppose it's not cyclic. In any case, we can draw the circle that passes through this point, and this point, the circumcircle of this triangle. And let us see where it intersects this line here. Now, since we assumed that the quadrilateral is not cyclic, it can't pass through this point. So let's assume it passes through this point here, which is on the extension of this segment in this direction. Now we know that this quadrilateral here, the extended one at this point, is cyclic, and so we can use its property that the sum of this angle and this angle is 180 degrees, and therefore this angle here is gamma. Now because this is gamma and this is gamma, then these 2 lines must be parallel, because for parallel lines, this angle equals this angle. But they're not parallel, they're intersecting in this point, which is a contradiction. And now if this point had been drawn inside of the segment, for example here, it would have been exactly the same. We would have had that this line is parallel to this line, which is obviously not true. They're again intersecting at this point. And so in any case, we get a contradiction. So our assumption was wrong, and the quadrilateral was cyclic in the first place. Now the proof for this case is completely analogous. Let us choose 3 points, for example, this point, and this point, and let's draw the circle around these 3 points. So if this circle passes through this point, then great, we're done. The quadrilateral is cyclic. If not, then it must intersect this line somewhere. So let us say it intersects it here. Now we know that this quadrilateral here, using the new point that we've added, is cyclic, because all the 4 points lie on the blue circle. And so we can use the property of cyclic quadrilaterals and mark this angle as gamma, because this angle and this angle both point towards this arc. But now, these 2 lines become parallel, because this angle equals this angle. And for such configuration, the lines must be parallel. But they're not parallel, they're intersecting at this point, which is a contradiction. In the same way, we could have proceeded if this point was on this segment somewhere, for example here. It's time for the optional problem. Suppose we have a quadrilateral and we draw the 4 angle bisectors of the 4 angles. So they form a quadrilateral like this. And we need to prove that this quadrilateral is cyclic. We need to prove that there exists a circle passing through all these 4 points. And here's the solution. Suppose that this angle is alpha, alpha. This is beta, beta. This is gamma, gamma. And this is delta, delta. Then we can apply the theorem for the sum of the angles in a triangle. For example, in this triangle, the sum of the angles is 180 degrees. And so this angle here, and respectively this angle, equals 180 minus alpha minus delta. Now for convenience, I'm going to draw a larger copy of the same quadrilateral here that we need to prove is cyclic. Now we can use the same theorem again in this triangle. And we get that this angle, which equals this angle, is 180 minus beta minus gamma. To prove that this quadrilateral is cyclic, we just need to show that the sum of this angle and this angle is 180 degrees. So we need to show that this equality here is true. But you can see that this statement is equivalent to this one. Well, let's see how we can prove this. Well, it is equivalent to this statement here. I just doubled the left-hand side and the right-hand side. But now look, the left-hand side is the sum of the angles of this quadrilateral. See, this angle is 2 times alpha, this is 2 times beta, 2 times gamma, 2 times delta. So their sum is this left-hand side. And we know that in any quadrilateral, we can split it into 2 triangles. And in each triangle, the sum of the angles is 180 degrees. And so the total sum of the angles in the quadrilateral will be 2 times 180 or 360. And therefore, this equality here is true because the left-hand side is the sum of the angles in the quadrilateral, and the right-hand side is the desired 360 degrees. Therefore, this is true, and therefore this is true, and therefore the sum of this angle and this angle is 180 degrees, which means that this quadrilateral, and respectively this quadrilateral, is cyclic.